everyone. Thank you for joining us today. I am Guillermo Varela from McNeil Europe, and I'm here today with Johanna Riad and Marco Pellegrino from Strusoft. Johanna works with user workflows in the Strusoft structural design software. She has a background in structural engineering, working mostly with tall buildings and large projects. And Marco Pellegrino is the product owner of the FEM-Design API and works with the development of both the Grasshopper and C# solutions. His background is also in structural engineering, and today they will present the Grasshopper plugin for the structural engineering software FEM-Design. There will be an overview on the functionality, user examples, and a step-by-step demo. You can download a free demo from the Rhino Package Manager or from Food for Rhino. I will share the link on the chat during the webinar if it's necessary, but you can open Rhino and download it from the Package Manager. Remember that in the last 15 minutes of this webinar, we will have some time for Q&A, so you can ask questions for them in the chat. And I think Marco is going to be answering them. If not, we can check them at the end of the webinar. Also, I would like to mention that the webinar is being recorded and will be available on our YouTube channel probably tomorrow, where you can find more webinars and tutorials. And that's all from my side. Thanks again, Johanna and Marco, for accepting the invitation to this webinar. And please start with the presentation when you're ready. Thank you.
Okay. Thank you very much, and thank you for the invitation to have us presenting with you today, Guillermo. It's a pleasure, and I think Marco and I have both been looking forward to showing our Grasshopper plugin to you. So yeah, let's get right into the presentation. You've already done the introduction, so let's go. Today we're going to be talking about the FEM-Design plugin to Grasshopper. And FEM-Design is a structural analysis software with FE analysis. And we're going to, I'm going to show a brief overview of our company and the program, and then go into a step-by-step demo of how it can be used. And at the end, show a bit more of an advanced example. And for the step-by-step demo to be as fun as possible for us, I think it would be nice if you can actually follow along with me while I do the live programming. So the first thing that I would like us to do is to download the two things that we will need to do this. So let me share my screen and I will show you. There we go. So in your browser, let's see, we can go to strusoft.com and scroll to FEM-Design and press Get a Free Trial. And in here, you can fill in your information, and at the end, press Submit. And in a minute or two, you will get an email with the instructions on how to download FEM-Design and also on how to activate your trial license. And I tried this on my computer previously. It took about 5 minutes. So it should be fine if you have a decent internet connection. So yeah, please, if you would like to follow along, just take a minute to do this at the beginning, and you could do the installation process at the same time as I'm presenting more general things about the company and so on. And the second thing that you will need is the FEM-Design Grasshopper plugin. And you can download that through the package manager in Rhino. So if we open up package manager and search for FEM-Design, you will find it here, and you can just press install for the latest version. The version you should install for FEM-Design is FEM-Design 23, which is the latest one. So that's good to know as well. So yeah, please do this as well if you want to follow along. And of course, if you don't have administrator rights or can't follow along today, then as Guillermo mentioned, the webinar will be recorded. So you can always watch this afterwards and do it then. Okay, so let me start by presenting a bit about our company and what we do while you're downloading and installing. So Strusoft was founded in 1982, but then it was actually a part of Skanska Software. So Skanska is a big construction company, and they had an in-house software group from 1982. But in 2002, the employees working on this, they bought the software free from Skanska and started Strusoft. And it's been an independent company working with structural analysis software since. And actually, in the last few years, we've expanded a bit. Our base is in Scandinavia, and that's where we were founded. In pretty much any structural engineering company in Sweden you go to, you will find that they are working with FEM-Design. But we're actually growing to Europe and the rest of the world now as well, which is exciting for us. Our major structural engineering software is FEM-Design, and it's a complete 3D FE analysis and design software where you can do anything you would like really as a structural engineer. So you can build small structures, big structures. It can be buildings or bridges or infrastructure. And you can do Eurocode design for timber, steel, concrete, and actually composite and masonry as well, and foundations. So it is mostly what you need in the one package. And to be able to follow along with the FEM-Design Grasshopper package, I think it makes sense that I show you just a general overview of how the program itself works. So let's jump out of the presentation and go to FEM-Design. Actually, the Zoom panels are hiding some of the things for me. So let's do this, and I hope that that looks better. Okay, let's work with this. So in FEM-Design, we have these major tabs that you will follow when you're creating a structure and loading and making an analysis. So let's just open up an example structure. Let's see. Let's see what I have. Can use this one. So this is what a building can look like when you've created it. And in the structure tab here on the left, you have all the things for creating a structure. So you have grid and stories, and you have different types of bars, shells, supports, etc. And that's what you use to create the geometry of the structure. In the second tab, you have the loads, and we have load cases and load combinations, as well as different type of loadings. So we have the normal point, line, and surface loads, but also more complex loading situations such as temperature and dynamic loading here on the end. In this tab, it's about the finite elements. So here you can change some settings and manually adjust the finite element mesh if you need to. A useful function here is peak smoothing that you can use to smooth out peak moments, for example. And this tab is for the analysis. So we use that to set up the analysis that we're going to do. So you can choose different types of analysis, both the static ones and dynamic. And for them, we can also change some settings and choose to make a linear analysis or nonlinear with second order effects or without. So you have all of those kinds of settings available here. Again, you don't need to follow along exactly on what it is, just showing you the overview. And after analysis, you have the design. So if we're looking at, for example, the concrete design, you can see here that we have, let's do, we have the option to draw different types of reinforcement for bars and for shells. And when you're doing a design, you have two major ways of working. You can choose checking all of the structural elements. So the answer you will get from that is a utilization ratio. And you can check if the structural objects pass or not. And you can also choose to do the auto design, where you will have FEM-Design choose the correct size of bars, for example, for you according to certain parameters that you set up. So those are the two major ways of using the design tabs. And just as an example, if we go back to the analysis tabs, we can also look at the results. They're in this panel here. We can look at, for example, the translational displacements and see how that looks. Or we can look at bar internal forces, another example. And you can change around the scaling of these, or look at what the values are and so on. So yeah, that's just like a general overview of the program, and I hope that's enough for you to be able to understand in general what it does. Okay, let's see. Let me go back to the presentation. So good to know about FEM-Design is also that you can connect to a number of different formats and other software. And what we're of course focusing on today is the Grasshopper connection, but that's just one of them. Before going into the live demo, I just want to show you a few examples that our customers have used this Grasshopper FEM-Design connection for, so that you can see a couple of different user cases. So first one, this is a wood hub. It's a building in Denmark, or actually it's a whole block of buildings. And in this FEM-Design Grasshopper plugin was used to handle data transfer between different FEM-Design models, because this is a huge structure, and it was divided into, I think, 5 or 6 different FEM-Design models, one for each building and also one for a large basement, which is placed underneath here. And the API was really useful for like efficiently moving loads and data around between those models. This is the Gothenburg big sports and music stadium. It's called Ullevi, and the Grasshopper API was used for this as well. And we're actually holding a webinar next month together with the one of the engineers of this, Alexander from WSP, so you can have a look out for that. But the plugin was in this case used to model the geometry of the stadium. And the project was looking at these cables that the roof is suspended from, and seeing if they need to be like replaced or not. That was the focus of the project. But it's not only big projects that we can use this for. We can also use it for structural parts, such as these stairs. And the stairs, I think we can all agree, are a very like parametric type of structure. So they can vary with the number of steps and the height and the length. And this was a project that we did in collaboration with the customer, actually, where we set up a parametric model for their different types of stairs. And that meant that they would not have to create a new calculation model every time that they had a new project where they manufactured these. And there's a similar example for agricultural tanks. We've seen actually several projects where parametric models have been used to create FEM-Design models for this type of structure. So yeah, big and small, different types of projects that you can use it for. Okay, so I hope that you've had some success with downloading the FEM-Design and the plugin, and we'll go into the live demo now. So Marco, please pay extra attention to the chat, and if someone has a problem, perhaps that you can help them out. But yeah, let's get into it. So let's open up Rhino. Actually, let me just see if I can hide this hide video panel for the okay. Perfect. I just needed to hide the Zoom stuff. So let's open up Grasshopper. And when you've successfully downloaded the plugin, you will find the new panel here that says FEM-Design. And just shortly before I start, you will find that the structure of this mirrors what you can see in FEM-Design quite a lot. So we have the different groups where you create geometry, for example, supports, bars, and shells. We have a separate group for the loads, and we have some other groups here for the analysis and the model, and also for the results. One important concept is deconstruct, which is used to, well, deconstruct elements. So if we look at, for example, the support group, when you're creating a support, it takes some inputs and it creates a point support. This is when you want to do the opposite thing. If you have an existing point support and you want to get the different data from it, you will use these deconstruct components. So that's good to know about those. There's one more concept that's good to mention briefly, and that is that we have two different ways of connecting to FEM-Design. So one is the regular way, where we send out a text file to FEM-Design, and it opens up, does some actions, and closes down again. And that's the way that our plugin has been working historically. But we now also have an option to connect to FEM-Design Live, and that's in the beta tab. This is actually going to be renamed in the next release. And what this does is it creates a live connection so that you can work with the model where you're doing some things manually and then some things through the API. So this is quite nice for a bit more interactive workflow. You need to use the older workflow if you want to do iterative analysis, because these components don't work so well if you're like using Rhino Compute or Hops, which I will show you at the end. Okay, so let's get into creating something. So yeah, please please follow along if you can. I'm going to start with creating a beam, and that is found under bars. And the first input that this needs is a curve, and we're going to create that from 2 points. So let's do this. And the second thing that we'll need is a material, and we'll find that here. So we're going to choose the component material database and place that in our on our canvas. Let's see. Okay, just took a minute. Let's see if I can hide this again. Yeah, maybe actually let's do this so we can see it at the same time. And the materials, we get all of them here, and we're going to choose a steel material for this example. So I'll choose list item, and I think I want this one. It's this. And the section, we can do the same thing. So we'll load the section database. And I'm going to show you another way of choosing the section. So you can do this section by name. And because it's a steel material, I'm going to choose a steel section. And I'll do the HEA 240. And we have a steel section there. And I'll plug that into the section component or the section input. So now we have a bar. These other inputs are not mandatory, so we'll just skip those for now. But of course, you will need to look at them if you're doing a real project. The next thing to do is create some supports. So actually, let's choose the one which is already set to hinged, so it's a bit easier. And we'll plug the 2 points into here. So we have a hinged point support at the start point and at the end point. And then I want to create a load. So I'll do a line load. And let's see. I think maybe I should do the draw full names. See. Because then it's easier if you miss it, you can always search for it. So let's create a line load, and I want that to be on the same line as the beam. So I'll use that, and I'll create a force. So let's choose something. And I want the same start force and end form because it's going to be end force because it's going to be a uniform load. And then one more thing we need for the load cases is, or for the load is load case. So I'm going to go to load case construct. And this one will need a name. So let's type LC1. And that goes in there. Okay, so now I have all the things that I need for my very simple model. I have a beam, I have point supports, I have a line load, and I have a load case. So then we'll move on to the model and model construct component. And what you need to do with this one is you need to plug the elements into structure elements here. Plug the line load into loads and the load case into load case. And a common mistake that I make all the time is I forget to flatten the structure elements. So as you can see now, we actually have 2 models. We don't want that, so we want to flatten this one. I'm going to go ahead and save now so that we have a copy of this. And then I'll start up the FEM-Design connection. So now it's time to go to the beta tab and choose FEM-Design connection. And when we place this component on the canvas, it's going to open up an instance of FEM-Design. And what we can do as a next step is to choose Open Model. And we'll plug the connection in, and then the model. And what this does is it opens up the model. So yeah, there we go. And we can check and see that, yeah, we do have a load, which looks good, and it's LC1. So everything is looking as expected, which is good. And the next thing that I want to do is I want to analyze this beam. So we'll go to beta again and choose FEM-Design Run Analysis. We can plug the connection in. And then we need to define an analysis. So we need to set those settings that I showed you previously in the program. And we actually find those here. So they're called analysis define. And these all have default settings. And from experience, I know that the only default setting I need to change is calculation of combination, because that's set to true by default, and we don't have any combinations in this model, so I need to set that to false. Otherwise, the calculate case is true, which is what we're interested in, and the rest of them are mostly false because they're a bit more unusual. So when I plug that in there, it's going to run the analysis. And we'll see that we have some results in the model. We didn't have those previously. The next thing that we can do is to retrieve some results. And we go to the beta tab again and choose get case comb results. That's one way of getting the results. And just to mention, when you're working with the plugin, you have to always tell the program what types of results that you want to get, because it doesn't do that automatically. That will be too data heavy if you have a big model. So the way it works is that you plug the connection in, and then you choose a result type. And in my case, I'm perhaps interested in the bar internal forces. So I choose that. And I can put several of these and choose different things, but it won't collect the results for anything else than what I ask for. So plug that in there, and then we should have some results. Something like that. And in order to be able to work with these in the Grasshopper environment, we need to deconstruct them. And for the results, we find the deconstruct component under results. So it's the bar internal force one. I'll plug the results in, and I need to tell it a case name. So it's LC1. And then we can see the different results in a format that makes more sense to us. And I can use these to create any type of visualization if I want to do that, for example. So we can do this and choose that. This is only working because I created my beam in the origin point. It actually gives you the positions along the beam. So if it's in another position, you would just have to translate the points to that position. But we could put the my as a z coordinate, for example, and we would have some kind of visualization of this. Maybe we want to scale it, or let's do this. And maybe you want to pick a color gradient and color this in some way, but I'll leave that to you. That's Grasshopper things. So of course you can do what you want with these results. Another thing to mention, we won't have time to show it in the example, but if you want to run design, you can do that from the API as well, and it's just this component FEM-Design run design that you need to choose. Okay, so I think that's it for the simpler demo. I hope it made sense to you, and I'll send this script to you after the webinar. So if you didn't manage to follow along with this quite quick typing, then you can get this and you can work with it from there. So let's move into a bit more advanced example. And that one, unfortunately, I don't have time to create it from the beginning. So I'll just open up a finished Grasshopper script and show you how it works instead. So let's open that. So this one. And I think this will take a little while to open up. But yeah, let me actually show you the the background of this example in schematic first. So this example is going to be about an iterative analysis. And there are, of course, many different situations where you need to work iteratively when you're a structural engineer. But this is based on a project that I actually worked with when I was still working with structural engineering. And it's quite a common scenario. We have a building that is going to be placed on top of some kind of basement. And in this case, the basement was a train tunnel, which is going to pass underneath of Gothenburg. And we have different engineering teams working on the building and on the tunnel. And an important thing here is to model the correct spring stiffness. It depends a bit on your structure, but in this case, it was important because the spring stiffness here will affect the loads that you need to apply to the top of the tunnel. And the stiffness of this will in turn affect what the correct spring stiffness is. So the way that you can go about this is to assume first the spring stiffness for the building model and run it. And you will take the reaction forces you get and place them as loads on top of the tunnel and run that tunnel model. And when you've done that, you will see that most likely the deformations that you have here and the deformations that you have here don't match at all. So you will set a new spring stiffness based on the force divided by the displacement. And you will again run the building model, apply the loads to the tunnel, and so on. And you will iterate this until you reach convergence. And the example I'm showing today, it's a very, very simplistic way of doing this, but it demonstrates how you can work with this concept. So let's get into the Grasshopper script. So this is the script in its entirety, so it's not too large to have time to go through. And let's start by looking at this part. So the first thing that I do in this script is I open an existing FEM-Design model, which is called building.str. I open that and I deconstruct it, and I deconstruct the supports and actually change the stiffness in the z direction for the support, and I have that as an input here. And because I have 3 supports, I have 3 numbers here, and the 100,000 is just a random guess. So let's trigger that first part of the script actually. So that's my model, and it's running. And when, in this case, because I'm doing an iteration, I'm working with the old way of connecting to FEM-Design, which means it will close down when it's done the things I've told it to do. And what we get here are some reaction forces, point support reactions that I will use to create some point loads. So you can see here that I've created 3 different point loads, and they are in the same position as the supports were. So I placed the building model and the tunnel model in the same coordinate system. If you don't have the same coordinate system, you would have to do some translation, of course. But yeah, then I add these point loads to the tunnel model. So I open up the tunnel model from this file path, and I add elements. So I add the loads, and then I run this model as well. So let's do that. Okay. And let's look at the results. Oops. So these are the results that I've gathered here in some panels. So the reaction forces we have here, and then we have the displacements from model 1 in the 3 different points, and the displacements from model 2. And as you can see, these don't match at all, which means that my random guess was wrong. And we need to make another iteration. So I will calculate a new guess for the support stiffness with this component. And the new guess is this. So I'll go to copy data only and go back and paste that in there. And that will trigger the second iteration. Okay, so second iteration is run, and let's go and look at the results. And as you can see now, my displacements from model 1 and model 2, they match a lot better. It hasn't quite converged, but they're they're better match now. And if I go again here and copy this and paste it to the beginning a couple of times more, then I'm pretty sure we'll have reached convergence. So it's quite nice already in itself. And of course, with this type of model, you could work with this workflow, but you could imagine that the copy and pasting will get a bit tiresome after a while. And there are actually ways that we can work with this in a little bit more automated way without having to leave our Grasshopper environment too much. So let's again see. Open up a new Grasshopper document. And we're going to use the hops component. And you can download that in the package manager as well. And what we'll do is right-click this and choose the path to our script. And the script I'm going to use is this one. It's a copy of the other script that I showed you. Let's see. Did I choose the wrong thing? Okay, this is not what it should look like. Let's see if I just open up my previous document instead. Maybe I did something wrong here. Yeah, it should, I don't know what I changed, but it should look like this. And what this actually contains is the script that I just showed you. So the input is the support stiffness, and the output is the new guess for spring stiffness. So if we go back to this, instead of having the data, the input data in a panel, I would plug an input like this into there. And I also have the context print, which is at the output side. And you will find those in utilities here, those components. So let's go back to this. So if I plug this in here, I will start my my iteration, but I don't want to do that because we don't have time. So I just wanted to show you how you can take this to the next level. Because when you do this, obviously you would still have to copy paste from this panel on the right to the panel on the left a few times, even if it's a bit easier when it's smaller like that. So I will right click this and choose export Python sample. And I'm going to show you what that looks like because I've already done that previously. Okay. So this is what it's going to look like, and it will give you the code to run hops in the Python environment. So what you can see here is that you have the Grasshopper evaluate definition, and it's pointing to the file path that I just showed you. And it's got the inputs here, and it's printing the outputs, I think, at the end here. Yeah. And the only thing that I would need to do from this point is to create a like Python for loop so that we have this running again and again with a new spring stiffness as an input, and then have some kind of convergence criteria for when this iteration should stop. And I've done that in a script previously, so I'll just open that up and show you. And that looks like this. So I'm no Python expert here, but I've created some variables for the previous stiffness and the current stiffness, and then a difference so that I'm checking the current iteration towards the previous one and seeing how big the difference is. And then I've set some type of tolerance for when I want the script to break. And it keeps running here and prints some data at the end of each iteration. And there's an if statement here that breaks the process when it has converged. So let's try if this works. I'm not sure it will. Let's actually see that I have thing here. We got the Rhino compute running. Yeah. Yeah, I think I'm not sure what I've done here, but it was the same error that we got before when I tried to show you how to create a hops component. So I must have changed something from when trying this earlier today. So I think we'll actually just have to skip that part. But in theory, this should work. And what it will do is it will run the Grasshopper script for you, and it will print the results here. And you could set this to start at the end of your working day, perhaps, and come back in the morning, and you will have the iterative analysis already finished. So I think that's a more neat way to work than the copy pasting that I showed you in the example. Yeah, it's a bit of a shame that it's not working, but yeah, I think I was messing around with some different Grasshopper plugins previously, and I must have broken something, so that's unfortunate. But anyway, let's go back to the end of the presentation. So yeah, to wrap this up, I want to mention that we have the trial that you just downloaded for FEM-Design. It's free for 14 days. And if you need more time to try it out, you can just contact Marco and I, and we can extend the trial period for you. And if you don't have FEM-Design already in your office, we can create a special offer for you for Grasshopper users, because we would like to get more users that use our API. So we negotiated with the sales team and got you a special offer. Also good to know is that we have documentation on this that you can just find by Googling FEM-Design API documentation. And there's also the possibility to work with FEM-Design through C#, which is if you prefer that for some reason. Another thing that's good to know is that we develop the API on demand, so it already contains most of the functionality within FEM-Design, But if there's something that you're missing and you're using it for a project, we can always try to develop the functionality that you need, so you won't have to wait for the next release. So I think that's a nice service that we can provide. Anything else? No, I think that's it. So thank you very much for listening, and please, any questions?
I think I will go through the question that the audience had.
Yeah.
I mean, there have been several questions about like American code. So unfortunately, we don't have yet the American code. We only allow, let's say, the Euro code mostly. So for that, we will need to wait. I know that there are some rumors that people are thinking of it. So my suggestion is please just raise it. Just raise the question again, and we will just report it to the technical people. Then there has been question about cable. So we don't support cable like for bigger displacement, but we support element for let's say compression only and tension only. So it really depends which kind of structure you need to analyze. And regarding iteration, I mean, the hops is definitely the nicest way to do it with the FEM-Design API. But it's worth mentioning that you can also use Galapagos, hops, Wallacey, I mean, all the kind of tool that use like genetic algorithm if you want. Then there has been some question from Tommaso, one of our super users, that was asking about visualization. So as you know, Grasshopper and Rhino is a CAD environment, and we like to see 3D object. I mean, Rhino is perfect for it. And with FEM-Design API, at the moment, we only support, let's say, stick elements. So if you want to see the 3D model of it, now we are relying on FEM-Design software. So basically, we just push the model to the graphical user interface, and you can see the model. But however, because our API goal is to share the data, I mean, all the data that the model has, you can quickly create the 3D model object on your own. And I shared a link through the chat where I show how to do it. Then there has been some question about the BHOM. Big fan about this open source project by Bro Happold, and we are not yet planned to implement the interoperability between FEM-Design and BHOM, but it might happen in the near future. And one really hot topic is Adiastatica connection. So Adiastatica, thanks to Nathan, a friend of mine, he developed a plugin in Grasshopper that allows the interoperability between data and Adiastatica. FEM-Design, it allows to save the model as SAF format. And Adiastatica can read this format. So the way to go from FEM-Design, let's say API, to Adiastatica is to just use this SAF format. So long story short, you go to FEM-Design, you do save as SAF, you open this file in Grasshopper, and you can go straight away to Adiastatica. So super, super easy.
Just adding to that, Marco, if you really love Grasshopper and you want to be in Grasshopper, you can also use that, as you mentioned, for the plugin. And that could be if you want to set up a workflow where you go all the way from like FEM-Design to Adiastatica and back again, it would be possible to do that as well. So just good to know.
Yeah, and theoretically speaking, I mean, if you are really, really nerdy, FEM-Design 2023, 23 is the latest. He has just unlocked the plastic shell analysis. So that means that now the steel material goes plastic, so you can see the redistribution of the forces. So if you have a really special connection, you can just do your own parametric connection with some scripting. But otherwise, just go to Adiastatica. And there are some questions about, can we use the package in Dynamo? I mean, this is a McNeil webinar. And I need to say that basically when I joined Strusoft, we used to have a Dynamo package, but unfortunately there were no so many users. And I was also not a big fan of it. So we stopped developing the tool for Dynamo. But however, I think we still have the Dynamo package for version 22, but we cannot work on it anymore. But one of the reasons to stop Dynamo package is because thanks to Rhino inside Rabbit, you can just use Grasshopper inside Rabbit. And that means that you can still have the FEM-Design API for Rabbit. I hope it's not a big issue. Yeah, then there is a question that maybe Johanna can reply. If there is what's the main difference between FEM-Design and ETABS or SAE SAP?
Yeah, it's a good question, and I think usually like we don't really like to like compare like this is what we're good at and this is what they're bad at, but it's like it's similar programs, and you can use FEM-Design for whatever you're using ETABS or SAP 2000 for. You can use FEM-Design. The user interface is a bit different. We think ours is easier, but the functionality in the program, I would say, is pretty much the same.
Probably the biggest difference is that we have our own API. So if something doesn't work, you can contact us. If something doesn't work with maybe SAP plugin that some external people has done, I mean, maybe they will not reply. So you can really rely on our work.
Yeah.
Well, thank you so much. I don't know if you want to add something, Marco?
No, it's worth mentioning that FEM-Design API has been released as an open source project. So we're really proud of it. So that means that if something happened to our team that maybe we don't reply because we forgot in some way, or maybe because we don't want to do this project anymore. I mean, it's open source, and that means that you can just fix the issue on your own. Or it also means that maybe you work for a big company, you just want to extend our work in some particular cases, you can just do it. And we know companies, especially some big one in Norway, that they have their own API based on our. So I think we are really happy to mention that it's open source.
That's right. Yeah. Well, so thank you so much, Johanna, for the presentation. Has been great to see all the projects and also the demo and how to use it. Has been really interesting. And thanks, Marco, for answering in the chat all the questions and for revisiting them now. It has been great to everyone to know if they haven't checked the chat. But yeah, thank you so much again for joining this webinar. I think it has been great, and we had a lot of viewers. As I said before, it's been recorded, so I will upload it to YouTube tomorrow. And Joanna is going to send the file with the Grasshopper definition, so I think you can check it and try the test version at least.
Yeah,
so
I'll send you the Python files as well, and hopefully you can manage to run them.
Great, thank you so much.
Right. Okay, thank you.
Thank you. Bye.
Have a good evening.
Have a nice day. You too. Bye bye.
Bye bye.